The traditional method of subnetting uses a fixed length subnet mask, or FLSM. But as you saw in part 1, borrowing 5 bits gave us a possibility of 32 subnets. But we only needed 24, which means we had 8 subnets left over. And that means we're wasting quite a few IP addresses. With fixed length subnet masking, each subnet created uses the same subnet mask and has the same number of IP addresses. Variable length subnet masks allow you to create subnets of different sizes, reducing the number of wasted IP addresses. To see how this works, let's go back to our first example, using a network address of 192.168.5.0/24. This time, we're going to plan out the number of addresses needed for each subnet. In this scenario, our accounting department needs 54 IP host addresses. Management needs 5, human resources requires 25, and sales needs 107. The first step is to create a table showing the different subnets that could be created if we borrowed some bits from the last octet. In this case, it's up to 6 bits. Next, it's easiest if you list the subnets in the order of hosts needed from highest to lowest. Now, all we need to do is to assign the subnet that'll provide the minimum number of addresses while wasting the least number of them. Since the sales network requires 107 hosts, the best choice is to assign it the /25 subnet, which has 126 host addresses available. Accounting only needs 54 hosts, so assigning it the /26 subnet works great. Human resources needs 25, so you can use /27. And finally, management only needs 5 host addresses, so the /29 network with its 6 available IP addresses is almost a perfect match. Another concept you need to know is how to find which network an IP address belongs to. This is done using a process called ANDing. For example, if you're given an IP address of 172.16.77.54/21, the first step is to convert the decimal number to its binary equivalent. Next, you need to convert the CIDR subnet notation, 21 in this case, to its binary equivalent. Remember that the /21 tells you there are 21 ones in the network ID, with 5 of those being borrowed from the third octet. This means that the subnet mask is 255.255.248.0. The value of 248 is derived by adding the value of the bits in the third octet. Now, let's use the ANDing process to determine the network address. This is done by multiplying each bit in the IP address with its matching bit in the subnet mask. Since anything times 0 is 0, this means that any bit in either the IP address or the subnet mask that's 0 results in an answer of 0. For each of these, a 0 is added to the ANDing result line. Likewise, since 1 times 1 is always 1, any bit that has a 1 in both the IP address and the subnet mask, when multiplied together, equals 1. So a 1 is added to the ANDing line. Now, to find the network ID, all we need to do is convert this new binary string to decimal, which in this case is 172.16.72.0. This means we've found that the IP address of 172.16.77.54/21 is part of the network called 172.16.72.0. Fixed-length subnet masking is used primarily in private networks, as it requires less configuration and administration. Variable-length subnet masking is more often used in public networks by large internet service providers, or ISPs. It's also important to note that variable-length subnet masking is only supported by advanced routing protocols, and configuring it can get pretty complex. One other concept you need to be aware of is supernetting. Supernetting has many advantages, including reducing routing table size, simplifying a network's overview, decreasing CPU and memory resources, and improving network performance. Supernetting is where we combine smaller pools of IP addresses to make a larger one. When supernetting, the main rule to remember is that network IDs must be in sequence to combine or summarize them. In other words, their network ID numbers must be contiguous. For example, we can supernet the networks 192.168.1.0, 2.0, and 3.0 because they're contiguous. But if our networks were 192.168.1.0, 4.0, and 5.0, we wouldn't be able to supernet all 3 of them together because they're not contiguous.